Hello everyone, my name is Yiran Zhao and I'm from Shanghai Jiao Tong University. It's my great pleasure to share our teamwork on ICDCS 2021. The paper we present today is Joint Order Dispatch and Repositioning for Urban Vehicle Sharing Systems with Robust Optimization. Our research is based on the observation that shared mobility has revolutionized the way people travel and commute. And this figure shows the modern life in a city. There are many shared mobilities, like the bike sharing, like Mobike, and the scooter sharing, like Zigzag, and the ride sharing, like Uber, and also the vehicle sharing that we research in this paper. And specifically, vehicle sharing is the service that passengers submit an order from application to the platform. Then the platform will dispatch a suitable vehicle to the passenger. Next, the passenger will go to rent the vehicle by himself and move freely in the city. And finally, the passenger will return the vehicle to a specific station. And obviously, vehicle sharing has many advantages. It can decrease the total number of vehicles in the city and facilitate citizens' life. But to fully unleash the power of the UVS system, there are many challenges. This figure shows the change of orders in Portland in a day. We notice that it changes over time, and also the uneven demand distribution lead to demand supply gaps, which deteriorate the order serving rate in an urban vehicle sharing system. And note that our UVS system is totally different from bike sharing system. In the UVS system, we need to consider the fuel load level of a vehicle. Specifically, when dispatching an order, the platform needs to consider the fuel load of vehicles. And when repositioning, the platform needs to consider the fuel consumption. As the result, algorithms in bike sharing system cannot be used directly in our UVS system. And then I will introduce the platform we focus on. Our platform is cloud-based UVS platform, and it takes two decisions. The first is order dispatch, and the second is repositioning. Note that these two decisions are not independent. The result of repositioning influence the number of vehicles that the platform can dispatch in the future, and the dispatch will influence the following repositioning. So we aim to design a joint order dispatch and repositioning scheme that maximize the UVS platform's long-term cumulative profit, given partial statistical knowledge about the demand distribution. And for the definition of partial statistical knowledge, I will introduce in the following slides. And we divide the planning horizon uniformly into different time slots. And in every time slot, the workflow of the platform is shown as follows. First, the platform will observe the number of each type vehicles available in each region. Then the platform reposition vehicles. Next, passengers submit orders to the platform. And finally, the platform allocates vehicles to orders. And in every time slot, the platform makes two decisions. The first is repositioning, denoted as RT, and the second is dispatch, denoted as WT. Here are the constraints they satisfy. And in every time slot, we aim to maximize the cumulative profit from the current time slot to the end of planning horizon. So the objective function has two parts. The first part is the immediate profit, which represents the profit that the platform can get in current time slot. And the second part is the expected future profits. Also, we need to update the available vehicle numbers. And to facilitate following analysis, we equivalently change the max profit problem to another mean cost problem. And the objective is cumulative cost now. The first part is the repositioning cost. The second part is the unserved order penalty. And the third part is the future cost. Note that here the demand distribution P is only partially known. From the math perspective, we define the partially known knowledge of the distributions as an ambiguity set. And specifically, the ambiguity set is the set of distributions. And the distributions in this set satisfy these constraints, like the expectation or the upper bound of the variance and extra. And our objective is changed to minimize the cost of the worst case in ambiguity set. In another word, it means minimize the maximum cost. This is why we call it robust optimization. And by integrating a series of methods involving distributionally robust optimization and primordial transformation, the original problem is changed to a second-order conic programming with finite number of constraints, and which can be solved by solvers like Cplex. And we validate our proposed methods using a large-scale real-world UVS dataset. And this figure shows that the overall cost of our method is much less than others. And this figure shows that our method serves more orders, thus obtains less penalty and do less repositioning, thus obtains less expense. And these hot maps represent the number of unserved orders. And it shows that our method serves more orders and is more stable as time going by. And for a conclusion, in general, we proposed a joint order dispatch and repositioning scheme that aims at maximizing the platform's cumulative profit in a UVS system. As in our model, the platform only has partial known information on the demand distribution, and we adopt this distributionally robust optimization where the platform's worst case profit over all possible distributions of demand is maximized. We then carry out a suite of transformation and finally convert the dynamic programming into a second-order conic programming, which can be solved efficiently. And we also carry out extensive experiment to validate the effectiveness of our proposed approach on a large-scale real-world vehicle sharing dataset. And our experiment results shows that the proposed long-term optimal approach achieves not only lower penalty, but also lower overall cost. Okay, thank you.